Welcome to the Hypnos Sleep Channel. Tonight, Hypnos, the ancient Greek god of sleep, will guide us gently through relaxing space facts about cosmic time, ancient light, distant galaxies, and the far future of the universe. The journey begins with the sky above Earth. At night, the stars can seem still, as if they have been pinned in place for us to look at whenever the world grows quiet. The moon returns. The planets wander slowly. The Milky Way, under a dark enough sky, lies across the darkness like a pale path of mist. But space is not still. The universe is changing in every direction. Light is traveling. Galaxies are shifting. Stars are spending their fuel. Old signals are stretching thinner. New stars are being born more slowly than they once were. And far beyond the reach of ordinary time, the universe has possible futures that are calm, strange, and not fully known. For now, imagine rising above Earth until the planet becomes a blue world beneath you. The atmosphere glows as a thin rim. The night side carries small amber lights. The moon waits nearby, close enough to guide tides, far enough that even light needs a little more than a second to cross the gap. That first delay is a gentle doorway into cosmic time. Moonlight is not quite now. Sunlight is older still, having traveled for about 8 minutes before touching Earth. Starlight may be years old. Galaxy light may be millions or billions of years old. The farther we look, the more the sky becomes a layered memory. Tonight's journey is not a countdown to an ending. It is a long, quiet walk through what space is doing. We will begin with the darkness between the stars, then move outward to ancient light, redshift, dark matter, the cosmic web, horizons, stars, black holes, and the possible futures that may wait beyond the bright age of galaxies. The universe is not gentle in the ordinary sense, but it is patient. It builds slowly, it reveals itself slowly, and it changes on scales so large that the mind can rest inside them without needing to solve them all at once. The first relaxing space fact is that the dark night sky is not a sign of emptiness. It is a sign of limits, distance, time, and the way light reaches us. If the universe were eternal, unchanging, and filled evenly with stars in every direction, the whole sky might be expected to glow. Every line of sight would eventually end on the surface of a star. This old puzzle is often called Olber's paradox. The real night sky is dark because the universe is not that simple. It has a finite age for arriving light. It is expanding, stars and galaxies evolve, and much light is shifted or hidden beyond what our eyes can see. Even inside the Milky Way, our eyes receive only a tiny sample. Under excellent dark skies, a person may see a few thousand stars at once, and several thousand across the whole sky over time. That sounds like a lot, until we remember that the Milky Way contains hundreds of billions of stars. Most are too faint, too distant, hidden by dust, or brightest in wavelengths our eyes cannot detect. Red dwarf stars make this lesson especially soft. They are small, cool, faint stars, and they are very common. Many can live for astonishingly long spans of time, far longer than the current age of the universe. Yet because they shine gently, they can hide in plain sight. The sky can be full of stars that are real, nearby by galactic standards, and still invisible to unaided eyes. Interstellar dust also changes the view. Dust does not make space dirty in an earthly way. It is made of tiny grains mixed with gas spread through the galaxy. It can dim and redden starlight, hiding parts of the Milky Way from visible eyes. Infrared telescopes can peer through some of that dust and reveal stars we would otherwise miss. So darkness is not nothing. Darkness can mean distance. It can mean faintness. It can mean dust. It can mean the universe has not had enough time to send every possible signal to us. It can mean that light has been stretched by expansion until it no longer arrives as visible light. Imagine the sky as a quiet room full of messages. Some messages are bright and close. Some are faint and old. Some are written in colors the human eye cannot read. Some have not arrived. Some will never arrive. The darkness between stars is not a blank page. It is the space between messages. This is a useful beginning because it turns the whole video away from fear and toward patience. We do not see everything. We never have. But what we do see is enough to begin reconstructing a story. Every astronomical observation is a message from an earlier time. The moon is close enough that the delay feels almost nothing, but even moonlight is not perfectly immediate. Sunlight takes about 8 minutes to reach Earth. The light from the nearest stars takes years. The light from the Andromeda galaxy takes about 2.5 million years. That means the sky is not arranged only by distance, it is arranged by memory. Nearby light is recent. Farther light is older. The deeper a telescope looks into space, the deeper it looks into the past. This can be imagined as mail with different delivery times. A letter from across the street arrives quickly. A letter from across an ocean takes longer. A letter from another era would be stranger still, arriving after the sender's world had changed. Starlight and galaxy light are like that, except the post office is space-time and the letters are photons. The analogy has limits because cosmic expansion changes the journey. A galaxy that emitted light billions of years ago may now be much farther away than a simple travel time calculation suggests. Still, the emotional truth remains helpful. Light preserves a record of where it came from and what happened to it along the way. When astronomers see a galaxy far away, they are not seeing that galaxy as it is at this instant. They are seeing the galaxy as it was when the light began its journey. Some galaxies appear young, messy, and active because we see them at an early stage of cosmic history. Other galaxies nearby appear older, more settled, or quieter because their light left more recently. This makes telescopes into time instruments. A telescope does not move us physically backward through time, but it collects old light. It allows the universe to show us earlier versions of itself. The past is not gone in the sky, it is still arriving. The gentle part is that Earth lives in a bright middle chapter. We are late enough for stars, galaxies, planets, and chemistry to exist. We are early enough that ancient light is still measurable, distant galaxies are still visible, and the universe's expansion can still be studied through many clues. So the night sky is both present and memory. You can look at the moon, the stars, and the distant galaxies, and each one is arriving from a different depth of time. Long before stars and galaxies, the universe was hot, dense, and filled with particles and radiation. Electrons were not yet settled around nuclei in the familiar way. Light could not travel freely over great distances because free electrons kept scattering photons. The young universe behaved like a glowing fog. Then, expansion cooled the universe. Electrons could bind with nuclei. Neutral atoms formed in large numbers. The fog cleared. Photons that had been trapped could travel freely. We observe that ancient light today as the cosmic microwave background, often spoken as CMB. The CMB is sometimes called a baby picture of the universe. That phrase is useful if handled gently. It is not an ordinary photograph. It does not show galaxies, stars, or planets. It is a map of ancient radiation with tiny temperature differences that reveal early patterns in matter, radiation, velocity, and gravity. Those differences were very small. The early universe was astonishingly smooth with faint ripples. Over time, gravity amplified the ripples. Matter gathered more strongly in some places than others. Eventually, the cosmic web, galaxies, clusters, stars, and planets grew from that unevenness. The CMB is also not the Big Bang itself. It is the oldest freely traveling electromagnetic light we can observe directly. It comes from the time when the universe became transparent, long after the earliest hot state. If the Big Bang is the deep beginning of the story, the CMB is more like the first page we can still read in light. Today, that ancient radiation has cooled to microwave wavelengths. It is nearly uniform across the sky, but not perfectly uniform. Instruments such as COBE, WMAP, and Planck measured it with increasing precision, turning a faint background into one of the richest records in cosmology. Imagine a vast pond that looks almost perfectly still. Only with careful measurement do you find tiny ripples. Those ripples are small, but given enough time, gravity can turn small differences into grand structure. The analogy is not exact because the early universe was not a two-dimensional pond, but the image helps keep the idea peaceful. As space expands, the CMB continues to cool. Its photons remain, but their wavelengths grow longer and their energy becomes weaker. In the far future, the ancient glow may become so faint that future observers cannot easily detect it. The universe will still carry its old light, but the message will be stretched thin. This is one of the most beautiful facts in space. The beginning is not only behind us. A cooled echo of it surrounds us from every direction. When light travels through an expanding universe, its wavelength can stretch. This stretching is called cosmological redshift. It is one of the main ways astronomers connect distance, expansion, and time. Redshift does not mean every galaxy is flying through space like a rocket moving away from us. On very large scales, the measured distance between unbound galaxies grows because the scale of the universe changes. Galaxies can have their own local motions, especially nearby. But across huge distances, a larger pattern appears. More distant galaxies generally show larger cosmological redshifts. The simplest image is a musical note lowered by a stretching journey. If the wave pattern is stretched, the note becomes lower. Light is not sound and space is not air, but the comparison gives the mind a handle. The wave arrives changed because the journey itself changed. Another image is a map whose scale changes with time. Two unbound locations may become farther apart, not because they are engines pushing through an empty room, but because the geometry used to measure their separation changes. This is safer than imagining space as literal rubber. Rubber has edges and stretches into a room outside itself. The universe does not need that kind of outside. Bound systems do not simply expand with the average cosmic scale. Atoms are held together. Planets remain bound to stars. Stars remain bound inside galaxies. Many galaxy groups remain bound by gravity. Expansion is a large-scale behavior, most clearly seen between systems that are not gravitationally tied together. This distinction keeps the script calm and accurate. The space between Earth and the Moon is not stretching in a way that pulls the Moon away as part of cosmic expansion. The solar system is not swelling with the universe. The Milky Way is not being torn apart by ordinary expansion. Local gravity and other forces hold local systems together. But beyond those local islands, expansion matters. The farther light travels through expanding space, the more its wavelength can be stretched. The color of a galaxy becomes a clue. The galaxy's spectrum becomes a record. The universe writes expansion into the light itself. Redshift is quiet evidence. It does not roar. It arrives as a subtle shift in wavelength, a soft lengthening of light from a distant place. Yet from that shift, astronomers learned that the universe is not static. It has a history, a scale, and a direction of change. Two of the most important unknowns in modern cosmology have similar names: dark matter and dark energy. They are easy to confuse, but they point to different mysteries. Dark matter is inferred through gravity. Galaxies rotate in ways that visible matter alone does not easily explain. Clusters of galaxies bend light through gravitational lensing. Hot gas in clusters, motions of galaxies, colliding clusters, and the growth of cosmic structure all suggest there is more gravitating matter than the light-emitting matter we can see. A gentle analogy is wind revealed by moving leaves. You may not see the wind itself, but you see leaves bending, grass leaning, and ripples moving across water. In a similar way, dark matter is inferred from what gravity does to stars, gas, galaxies, and light. The analogy has limits because wind is ordinary matter, and dark matter is not known to be ordinary hidden dust. But it helps keep the inference clear. Dark energy is different. It is the label for the unknown cause or effective component associated with the accelerated expansion of the universe. Observations of distant supernovae, the CMB, baryon acoustic oscillations, and galaxy structure all support the idea that cosmic expansion has been accelerating in the late universe. Dark matter tends to gather and help build structure. Dark energy, in the standard picture, is comparatively smooth and affects expansion on very large scales. Dark matter is more like gravitational scaffolding. Dark energy is connected to the changing scale of the cosmos. Neither image is perfect, but the distinction matters. In the common lambda CDM model, the cosmic inventory is often described as a small fraction ordinary matter, a larger fraction dark matter, and an even larger fraction dark energy. Those numbers depend on the model and measurements, so a sleep script does not need to recite them repeatedly. The important idea is simpler. The visible stars, planets, gas, and dust are only one part of the cosmic accounting. This could feel unsettling, but it can also feel spacious. The universe is not less beautiful because much of it is inferred rather than directly seen. In fact, inference is part of the beauty. Science learns from motion, bending light, patterns in ancient radiation, and the way galaxies gather. Dark matter and dark energy remind us that the universe is not limited to what glows. Some of its deepest features are known by their effects, like a silent current revealed by the path of floating leaves. On the largest scales, galaxies are not sprinkled evenly through space. Surveys reveal a cosmic web: filaments, sheets, dense nodes, galaxy clusters, and enormous voids. The universe has structure, but not like a building or a solid net. It is a three-dimensional pattern of matter shaped by gravity over billions of years. The early universe began with tiny density differences. Gravity slowly amplified them. Regions with slightly more matter attracted more matter. Regions with less matter became emptier by comparison. Over time, galaxies and dark matter gathered along filaments and nodes while voids opened between them. One safe image is a nighttime transportation map. Galaxy clusters resemble bright cities at junctions. Filaments resemble long routes between them. Voids are quieter regions between the routes. The map was not designed, and the web is not flat, but the image gives the mind a way to see it. Voids are especially restful if described accurately. A cosmic void is not truly empty. It may contain some galaxies, gas, dark matter, and faint material, but much less than average. Voids can span tens to hundreds of millions of light-years, depending on how they are defined. They are not holes in reality. They are underdense regions, part of the pattern. The web needs its quiet spaces. A musical score needs rests as well as notes. A landscape needs valleys as well as ridges. The cosmic web is made by contrast, denser filaments and emptier voids, bright clusters and dimmer expanses. This structure also helps us understand the future. Gravity gathers locally. Expansion affects the large-scale distances between unbound regions. Some neighborhoods become tied together, while the space between larger regions grows. The universe can be both gathering and separating, depending on the scale. Imagine floating far above the cosmic web, if such a viewpoint were possible. Galaxies would not look like isolated jewels scattered randomly. They would trace luminous threads and knots. Between the threads, huge, quiet regions would open like dark lakes. The cosmic web is a reminder that the universe is not merely a collection of objects. It is a landscape of relationships. Galaxies have histories. They are not permanent shapes painted on the sky. They grow through gas inflow, star formation, mergers, tidal stripping, and interactions with smaller companions. When galaxies merge, individual stars almost never collide because the distances between stars are enormous compared with stellar sizes. Two galaxies can pass through each other more like sparse swarms than solid objects. Their gas, however, can collide, compress, heat, and form new stars. Gravity rearranges orbits. Spiral shapes can be disturbed. Tidal streams can be pulled out like loose threads from cloth. The Milky Way carries evidence of past accretion events. It continues to interact with smaller companions, including dwarf galaxies. The Magellanic Clouds are visible reminders that our galaxy is not alone. The Sagittarius system and other streams show that smaller galaxies can be stretched and partly absorbed. This gives the Milky Way a memory. Not a conscious memory, of course, but a physical record written in star motions, chemistry, streams, and halo structure. A galaxy is not only what it looks like tonight, it is a record of what it has eaten, attracted, formed, and survived. Our future local sky has its own slow transformation. The Milky Way and Andromeda are moving toward one another and are expected to merge over deep time. This does not mean stars will crash like sparks. It means two vast systems will pass, pull, distort, and eventually settle into a new combined galaxy. During that future, the wider universe may continue expanding. Local gravity can bind the local group while more distant galaxies drift beyond practical reach. So one island grows more merged and complex, while the far ocean becomes harder to see. This is one of the quiet patterns in cosmology. Small scales and large scales do not always tell the same story. Gravity can gather a neighborhood, expansion can isolate that neighborhood from other neighborhoods. The same universe can be intimate nearby and unreachable far away. Galaxies are therefore not just background scenery. They are living histories of motion, gravity, gas, dark matter, and time. The early universe did not contain the full chemical richness needed for planets like Earth. In the beginning, it was mostly hydrogen and helium, with only traces of light nuclei. There was no familiar supply of carbon, oxygen, silicon, calcium, or iron in the quantities needed for rocks, oceans, atmospheres, and living bodies. Stars changed that. Different stellar processes built different elements. Carbon can be made through helium burning in stars. Oxygen is strongly associated with massive stars. Iron group elements arise through multiple pathways, including advanced burning and explosive processes. Stellar winds, planetary nebulae, supernovae, and other ejecta returned enriched material to interstellar space. A useful image is a growing alphabet. The early universe had only a few letters for chemistry. Stars added more letters over time. With a richer alphabet, nature could write more complicated chemical words: minerals, dust grains, rocky planets, water, atmospheres, and eventually the chemistry of life. The image has limits. Chemistry is not free-form writing, and complexity does not guarantee life. But it captures the slow enrichment of the cosmos. The universe had to become chemically interesting before a world like Earth could exist. This also softens the famous phrase that we are made of stardust. It is beautiful, but it needs care. Many elements in our bodies were forged by stars or stellar explosions, while much hydrogen predates the stars. We are not made entirely of material cooked inside stars. We are made from several cosmic sources: primordial hydrogen, stellar carbon and oxygen, heavier elements from different astrophysical pathways, and recycled matter that pass through gas, dust, stars, asteroids, and planets. Earth formed from a solar nebula already enriched by earlier generations of stars. The atoms in the ground were not created specifically for Earth. Earth is more like a city rebuilt from older bricks, except some bricks were changed in cosmic furnaces before they arrived. This gives the far future story a deeper middle. The universe is not only cooling, it also spent billions of years becoming capable of rocks, water, and life. The future matters because the present is so richly assembled. The observable universe is the region from which light has had time to reach us. It is centered on every observer's own location because every observer has their own past light cone. This does not make Earth the center of all reality. It simply means Earth is the center of our view. The observable universe is not the same as the whole universe. It is a horizon of information. Beyond it may be more universe, perhaps much more, but light from those regions has not reached us. The boundary is not a physical wall. It is more like the limit of a view across an ocean. The scale is strange because the universe expanded while the oldest light traveled. The universe is about 13.8 billion years old, but the observable universe is far larger than 13.8 billion light-years across in present-day co-moving distance. Public explanations often give a diameter around 92 to 93 billion light-years. This does not mean the universe is 93 billion years old. It means space changed while light was on its way. The cosmic microwave background comes from a last scattering surface in our past light cone. It is not a shell we could fly to and touch. It surrounds our view because wherever we look back to a time when the observable universe was hot, dense, and glowing. There are different kinds of horizons. The particle horizon asks what light could have reached us so far. The event horizon asks what signals emitted now might ever reach us in an accelerating universe. The Hubble sphere is another related but different concept. A sleep-friendly script does not need to dwell on the technical boundaries. but it should not turn them into one simple edge. The emotional value is humility. Knowledge has a horizon. The horizon gives the view its shape. Not everything real can be reached, and not everything beyond reach is lost. Some of it simply belongs to a larger silence. When we look outward, we are always looking from somewhere, and the universe gives each somewhere its own circle of arriving news. Black holes are among the most durable structures we know how to describe. A stellar mass black hole may form from the collapse of a massive star. Supermassive black holes sit in the centers of galaxies with masses of millions or billions of suns. They do not shine by themselves, but gas outside their event horizons can become intensely bright. A black hole is not a cosmic vacuum cleaner. It does not automatically pull in everything around it. Far away, its gravity acts like the gravity of any other object with the same mass. What makes a black hole special is that inside the event horizon, escape paths close. Time near black holes also teaches care. To a distant observer, signals from something approaching an idealized event horizon arrive increasingly delayed and redshifted. The falling object can seem to fade and freeze near the horizon, but locally, the falling observer's own clock ticks normally. The freezing is about received signals and coordinates, not about the traveler feeling time stop. Black holes may matter for the far future because they can outlast ordinary stars. After star formation declines and many stellar remnants have cooled, black holes may remain as some of the last large gravitational landmarks. Yet even black holes may not be permanent. Hawking radiation is a quantum prediction that black holes emit radiation and very slowly lose energy. This has not been directly observed from astrophysical black holes, and for large black holes, the timescale is far beyond the present age of the universe. The important phrase is very slowly. Imagine a deep reservoir in winter, releasing one faint thread of mist over an impossible span of time. That is not a literal picture, but it keeps the scale gentle. A black hole is not merely an ending. In theory, it can also be part of a longer transformation. Black hole entropy adds another quiet mystery. The entropy of a black hole is related to the area of its horizon, not the volume inside in an ordinary way. That fact has helped physicists think about information, geometry, and the deep structure of space-time. We do not need the equations here. The sleep-friendly version is this. Black holes suggest that space, time, gravity, and information may be tied together more deeply than everyday experience reveals. In the far future, black holes may be the last dark punctuation marks in the cosmic sentence, holding their silence for ages before even that silence changes. Stars do not all age the same way. Massive stars live quickly and end dramatically. Sun-like stars live more quietly, swell later in life, shed outer layers, and leave white dwarfs. Smaller red dwarfs live so slowly that none have yet reached the end of their full lifetimes, because the universe is too young. This gives the future many stages. First, the bright, massive stars vanish because they spend fuel rapidly. Star formation continues, but slows as galaxies use, heat, or lose the gas needed to make new stars. Over time, the sky becomes dominated by longer-lived, dimmer stars. Red dwarfs may be the long candlelight of the future universe. They can shine gently for trillions of years in theoretical models. Around some of them, planets may remain for unimaginable spans. Their light is faint, but their patience is extraordinary. White dwarfs are another future. They are dense stellar remnants, no longer producing energy by ordinary fusion in their cores. They cool slowly. Over enough time, they may become black dwarfs, cold remnants that no longer shine significantly. The universe is not old enough for true black dwarfs to exist yet, so black dwarfs are a future prediction, not a present population. This is a perfect Hypnos fact because it asks us to hold absence gently. A black dwarf is not an explosion. It is not a catastrophe. It is the final cooling of something that once shone. A star becomes a remnant, and the remnant releases its remaining warmth into space. Neutron stars may remain too, incredibly dense and small compared with ordinary stars. Some will cool, some may merge, some may persist as silent objects. Planets, asteroids, and fragments may drift through darkened systems. The architecture of old stellar systems may continue long after the familiar glow is gone. The far future is therefore not one scene. It is a sequence: bright stars, dim stars, remnants, cooling, separation, and deepening quiet. Heat death is one of the most misunderstood phrases in cosmology. It does not mean the universe burns. It means usable energy differences gradually disappear. Energy may still exist, but if it is too evenly spread, it cannot easily drive complex change. A simple analogy is a battery whose terminals have reached the same potential. The battery may still contain energy in some sense, but without a useful difference, it cannot power a device. The analogy is limited because cosmic thermodynamics includes gravity, horizons, quantum fields, and expansion, but it gives the core idea. Stars shine because there are energy gradients. Planets have weather because sunlight warms some regions more than others. Life uses chemical and thermal differences. Motion, metabolism, climate, and engines all depend on differences. In a heat-death-like future, the universe trends toward fewer useful differences. Stars have burned out. New stars are rare or absent. Matter is spread thin or locked into remnants. Black holes may slowly evaporate. Radiation is stretched to longer and longer wavelengths. The old structures that made the universe lively become harder to sustain. This is not known as an absolutely guaranteed script for reality. It depends on the behavior of dark energy, particle physics, gravity, and assumptions about the far future. But within standard broad expectations, it is a leading way to imagine the universe becoming quieter. The tone should stay peaceful. Heat death is not a monster waiting at the end of time. It is more like a lake after every ripple has spread out. The water remains, but the motion that made patterns has softened. This future also changes the meaning of time. If very little changes, time may still exist as part of the description, but there are fewer clocks, fewer cycles, fewer events, and fewer stories. The universe does not need to end in a single moment for the familiar drama of change to fade. The calm fact is that endings in cosmology may not be events. Some are limits, some are fades, some are changes in what can happen. The big freeze and heat death are not the only ideas about the future. Some models explore other possibilities, and each should be held with the right amount of uncertainty. The Big Rip is one possibility if dark energy behaves in a certain extreme way. Expansion would strengthen until it overcame more and more bound structures. Galaxy clusters would separate, then galaxies, then smaller systems. This is not the ordinary assumption, but it shows how important dark energy is to the future. Vacuum decay is stranger. In some theoretical pictures, the universe may occupy a state that appears stable but is not the lowest possible energy state. A transition to a lower state could change the rules of physics inside an expanding bubble. This is highly speculative for a sleep script, and it should be presented as a theoretical edge, not a practical worry. Cyclic models imagine that the universe may not have one final ending. Some involve bounces, repeating phases, or larger frameworks in which universes can emerge more than once. These ideas are not settled facts. They are ways scientists think about the boundary between evidence and possibility. Inflation belongs to a similar careful category when discussing the earliest universe. Inflationary models can explain why the observable universe is so uniform and why tiny early perturbations existed, but the exact physical mechanism has not been directly identified. It is powerful, useful, and still incomplete. The same humility applies when speaking about the Big Bang. In standard cosmology, the hot Big Bang was not an explosion from one point into empty space. It was an early hot, dense state of the observable universe, with expansion happening everywhere. Extrapolating backward reaches a limit where classical general relativity breaks down. That limit does not mean physics knows every detail of the absolute beginning. These uncertainties make the universe more interesting, not less. Science is not weakened by saying what is unknown. It becomes more trustworthy. A calm listener can rest inside the distinction between measured evidence, model-based extrapolation, and open speculation. The far future may be a freeze, a fade, a rip, a transition, a renewal, or something no current model has fully captured. The universe is larger than our certainty. After traveling through ancient light and distant futures, it helps to come back to the present sky. The stars above Earth are temporary, but they are here now. The moon is close, but still delayed by light. The sun is ordinary as a star, but everything alive on Earth depends on its steady warmth. The Milky Way is not a static painting. It is a galaxy with a disk, bulge, halo, gas, dust, dark matter, star-forming regions, old stars, young stars, streams, and a central black hole called Sagittarius, a star. The Sun sits far from the galactic center, in a local region of the disk, moving with the galaxy on a path that takes hundreds of millions of years to complete one orbit. Beyond the Milky Way is the local group, Andromeda, Triangulum, dwarf galaxies, streams, and small companions. Beyond that are clusters, superclusters, flow-defined regions, filaments, and voids. The universe becomes less like a set of isolated objects and more like a landscape of motion. And yet, from Earth, it returns to simplicity. A quiet room, a dark window, a few visible stars, a moon whose light is just over a second old, a planet turning gently beneath you. This is the strange gift of space facts. They make the room larger without making it less familiar. The water in a glass contains hydrogen from the early universe and oxygen from stellar history. The calcium in bones, the carbon in cells, and the iron in blood belong to different cosmic workshops. The body is local, but its ingredients are ancient. The far future of the universe can feel impossibly distant, but the same processes are already present in softer forms. Light travels, energy spreads, stars age, gravity gathers, expansion widens the gaps between unbound regions. The universe is always becoming. The final relaxing space fact is this: we live in a brief, bright chapter, able to look up and receive messages from many other chapters. We cannot see everything. We cannot know every ending, but we can listen to the light that has arrived. Before returning fully to Earth, it helps to pause inside the solar system. It is the first large scale that still feels almost familiar. The Sun is our local star. Earth orbits at about 1 astronomical unit, and sunlight takes about 8 minutes to arrive. That means the warmth on your skin is always a message from the recent past. The moon gives the first breath of delay. Light crosses the Earth-Moon gap in a little more than a second. Human spacecraft needed days. That difference between light time and travel time becomes one of the calmest ways to understand scale. Space is not only distance, space is waiting. Farther outward, the delays widen. Sunlight takes much longer to reach the outer planets. Neptune receives sunlight after a journey of hours. The sun is still bright there, but it is a smaller lamp in a much larger room. The edge of the solar system is not a wall. The heliopause is a transition where the solar wind gives way to interstellar space. Voyager 1 crossed into that region, becoming a human-made object outside the sun's main bubble. But even after that crossing, it was not near another star. It had only stepped out of the front garden of the solar system, while the first true neighboring star remained years away for light and tens of thousands of years away for Voyager-like travel. This is why the solar system is such a good bridge between home and the galaxy. It is large enough to humble the mind, but still organized around one familiar star. Planets move in long paths. Comets sleep in distant reservoirs and wake near the sun. Dust, asteroids, moons, and icy bodies preserve pieces of older history. If the sun were shrunk to a tiny dot, Earth would become a speck nearby, and Neptune would still sit several meters away. But Proxima Centauri, the nearest known star to the sun, would be far beyond the room, far beyond the street, far beyond ordinary intuition. Shrinking the sun does not make the space between stars manageable. It only reveals how empty the stellar neighborhood is. The solar system teaches the first quiet rule of scale. A place can be home and still be enormous. A star can be familiar and still be almost unreachable in its outer reaches. A spacecraft can be the farthest thing we have sent and still be barely beginning the interstellar journey. The Milky Way is not only a white band across the sky. It is our home galaxy, a barred spiral system with a disk, bulge, halo, gas, dust, dark matter, star-forming regions, old stars, young stars, and a central black hole. We see it from inside, which makes it both intimate and difficult to picture. The sun is not near the center. It lives in a local region of the galactic disk, far from Sagittarius A star, the compact radio source associated with the Milky Way's central supermassive black hole. Around the center, stars move in orbits that reveal a hidden mass of about millions of suns. The event. Horizon telescope image of Sagittarius. A star shows light from the region around the black hole, not the event horizon as a visible surface. The Milky Way is often described as about 100,000 light-years across, though its edges are not clean walls. It has a disk of stars and gas, a central bulge, a halo, and an extended dark matter halo inferred through gravity. The Sun takes hundreds of millions of years to complete one orbit around the galactic center. One galactic year is longer than the time since dinosaurs first appeared and vanished from Earth. From inside the galaxy, the Milky Way can feel like weather made of stars. Dust lanes cross the bright band. Star clouds thicken toward the center. Dark patches hide light from behind them. The galaxy is not a flat picture. It is a layered city, and we live inside one neighborhood of it. This helps with the future of the universe because the Milky Way is both a local home and a future island. Local gravity can bind the galaxy and its neighbors, while cosmic expansion carries more distant systems away. The far future may not erase the local sky immediately. It may first make the wider sky less available. The Milky Way also carries chemical memory. Some stars are old and poor in heavier elements, others formed from gas enriched by earlier generations. The galaxy has streams from smaller companions, scars of older interactions, and regions where gas still forms new stars. So, when we speak of the universe growing quieter, we are not talking about a blank darkness arriving tomorrow. We are talking about a home galaxy with a long history and a long future, slowly changing in a universe whose largest distances continue to widen. Beyond the Milky Way is the Local Group, a small family of galaxies dominated by the Milky Way and Andromeda, with Triangulum and many dwarf galaxies. Dwarf galaxies are not side notes. They are numerous, quiet companions, often faint and easily overlooked. Andromeda is often called our nearest large spiral galaxy, about 2.5 million light-years away. That phrase, nearby galaxy, is wonderfully strange. Nearby, in galactic language, still means light has traveled for millions of years. When we look at Andromeda, we see it as it was before modern humans, before cities, before the familiar history of Earth. The Local Group spans millions of light-years. It is not a tight room of galaxies. It is more like an archipelago with great dark channels between islands. The Milky Way and Andromeda are moving toward one another, and over deep time, they are expected to merge. Most stars will still miss one another because galaxies are sparse, but gravity will rearrange the whole system. Farther out, there are galaxy groups, galaxy clusters, superclusters, and flow-defined regions. A cluster can contain many galaxies, hot gas, and dark matter. A supercluster is a broader association whose boundaries may not be sharp and may not be gravitationally bound as one object. Laniakea, for example, is best understood as a flow-defined region, a basin of motion, not a solid cosmic country. At these scales, the universe becomes a landscape of motion. Galaxies fall toward denser regions, clusters gather at nodes, filaments connect structures, voids open between them. The great attractor is not one simple object, but a broad, gravitationally influential region, part of a larger pattern of flows. This context matters for the far future because expansion and gravity are both at work. Bound systems can remain together. Unbound distant systems can become increasingly unreachable. The Local Group may become more merged and self-contained while faraway galaxies pass beyond practical observability. The listener can picture standing on a future world under a sky still rich with local stars, while the grander cosmic web has faded from view. Not because it stopped existing, but because expansion placed it beyond the reach of arriving light. One of the most surprising scale facts is that the observable universe is much larger than 13.8 billion light-years across, even though the universe is about 13.8 billion years old. The reason is expansion. The light traveled while space itself was changing. In broad public language, the observable universe is often described as about 92 to 93 billion light-years across in present-day Khamoving diameter. This does not mean light has traveled for 93 billion years. It means the regions that emitted the oldest observable light are now much farther away than they were when that light began its journey. This is a beautiful place to slow down. Imagine receiving an old letter from a house. During the letter's journey, the road stretched, the town expanded, and the house moved farther away in the changing map. The letter's travel time and the house's present distance are not the same number. The observable universe is also not the whole universe. The whole universe may be much larger than what we can see, and it may even be infinite. But those are not observed facts in the simple way the observable horizon is. Our view is bounded by the age of arriving light, expansion, and the structure of space-time. Every observer has their own observable universe, centered on their location. This does not make every observer the special center of everything. It means every observer receives a different circle of cosmic news. The center is the receiver, not necessarily the center of reality. The cosmic microwave background sits near the limit of ordinary electromagnetic vision, but it is not a wall. It is a last scattering surface in our past light cone, an ancient glow from every direction. We cannot fly to it as a destination because it is not an object sitting at the edge. It is a time in the universe's history seen from where we are. This is why the observable universe feels like a horizon over an ocean. The horizon is real as a limit to view, but it is not proof that nothing lies beyond. The beauty is not in pretending to see everything. The beauty is in knowing exactly what kind of view we have. The future of the universe can be imagined in eras rather than a single ending. First comes the current bright age, when stars are common and galaxies still shine. Star formation continues, but the overall rate has declined from its ancient peak. The universe once made stars more vigorously than it does today. Later, gas becomes less available for new stars. Massive stars vanish quickly. Sun-like stars leave white dwarfs. Red dwarfs continue shining for enormous spans. The sky becomes dimmer, redder, and quieter, but not instantly dark. After that, stellar remnants become more important than shining stars. White dwarfs cool. Neutron stars and black holes remain. Planets and smaller bodies may continue orbiting remnants or drift after gravitational encounters. Systems become older, sparser, and less active. If proton decay exists, it could change the fate of matter over extreme times. But proton decay has not been observed. If protons are stable, some remnants may persist differently. This is why the far future must be spoken with care. At extreme times, cosmology depends on particle physics we do not fully know. Black holes may dominate an even later era. They can persist for lengths of time that make stellar lifetimes seem brief. Hawking radiation suggests that black holes slowly evaporate, but astrophysical black holes are far too cold and massive for this to be observed directly now. The prediction belongs to the meeting place of gravity, quantum theory, and deep time. Eventually, if the universe follows a heat-death-like path, usable differences become scarce. Radiation is stretched. Matter is thin or locked in remnants. Events become rare. Time still belongs to the description, but the universe has fewer ways to mark it. This layered future is more sleep-friendly than a single dramatic end. It is not a cliff. It is a long shore, with waves arriving farther and farther apart. After all these future possibilities, the present universe becomes more precious. We live after the first stars enriched space, after galaxies formed, after rocky planets became possible, after Earth cooled, after life appeared, and after intelligence learned to build telescopes. But we also live before the cosmic microwave background has faded beyond practical reach, before distant galaxies have all slipped past our event horizon, before the bright age of stars is over, and before the sky has become far more isolated. This is a rare middle chapter. The universe is old enough to be complex and young enough to be readable. It contains ancient light, but the ancient light has not yet vanished into undetectability. It contains distant galaxies, but many are still visible. It contains enough star formation to keep galaxies alive with new light, but enough history for planets and life to exist. That balance is not something the universe arranged for us. It is simply where we happen to be. but it gives the sky a special tenderness. A telescope today can gather evidence of the early universe, galaxy evolution, dark matter, dark energy, black holes, chemical enrichment, and expansion. Future observers may have fewer clues. Earlier observers would not have existed before the chemistry of life was possible. So the present sky is not merely a backdrop, it is an opportunity. It is a temporary window in which the universe can look back at itself through living minds on a small planet. The peaceful conclusion is not that we understand everything. We do not. Dark matter remains unidentified. Dark energy remains mysterious. The total universe may extend far beyond our view. The exact far future is uncertain. But uncertainty does not erase wonder. It gives wonder room to breathe. The sky tonight is temporary, incomplete, and still enough. It carries messages from the moon, the sun, the stars, the galaxies, and the oldest light we can observe. That is more than enough for one quiet night. One of the quietest far future ideas is that later observers may have less evidence than we do. The universe may still exist. Local stars may still shine for a time. A future galaxy may still contain planets, remnants, and old systems. But the wider evidence of cosmic expansion could become harder to see. In a universe dominated by accelerated expansion, distant, unbound galaxies can pass beyond practical observability. Their light becomes stretched, delayed, and weakened. The cosmic microwave background cools and lengthens. The grand web beyond the local bound region becomes less accessible. A future astronomer inside a merged local group remnant might look up and see a sky rich with local stars, but not the deep field of galaxies that telescopes reveal today. They might not easily measure the same ancient glow. They might not have the same obvious evidence that the universe was once hot, dense, and filled with early radiation. This does not mean science ends. Future observers could still study local stars, remnants, gravity, black holes, chemistry, and their own galaxy. But the universe's early story may be more difficult to reconstruct. The clues available to any civilization depend on when that civilization appears. That thought makes our present moment feel delicate. We are not only living in a bright era, we are living in an era when the universe is still talkative. The CMB can still be measured. Distant galaxies still arrive as old light. Redshift still paints expansion into spectra. Galaxy surveys still trace the cosmic web. The sky still carries many layers of evidence at once. It is like walking along a beach before the tide erases the footprints. The footprints are not permanent, and they were not placed there for us. But while they remain, they tell a story. Later, the beach may still be beautiful, but the older trail may be harder to follow. This is why cosmic horizons are not only boundaries of distance, they are boundaries of historical memory. The universe may keep changing in ways that make parts of its own past less visible. The peaceful lesson is not to worry about the loss, it is to value the view. Tonight, under this sky, the universe is still full of arriving messages. Some are recent, some are ancient, some are faint, some are incomplete. Together, they give us a rare chance to hear the long history of space before the music grows quieter. Now imagine drifting back from the largest scales, past the cosmic web with its filaments and quiet voids, past galaxy clusters and local islands, past Andromeda, past the Milky Way's halo, and down toward the familiar glow of the sun. Earth appears again as a blue world. Clouds move over oceans. deserts hold warmth, forests darken with night. The moon keeps its patient place, and the stars continue their long, silent work above the atmosphere. Nothing in this journey needs to be hurried. The oldest light has traveled for ages. The stars spend their fuel slowly. The galaxies move in deep time. The future of the universe, whatever it becomes, unfolds far beyond the scale of a single night. So the sky can hold two truths at once. It is temporary because every star and galaxy belongs to time. And it is peaceful because its changes are almost unimaginably slow. You are part of this same universe, made of old matter, warmed by a star, resting on a planet that carries ancient chemistry. The space above you is not empty. It is memory, motion, distance, gravity, light, and time. And while Earth turns beneath the quiet stars, the universe continues its long unfolding, not loudly, not urgently, just patiently, through redshift, starlight, cooling, gravity, and the soft dark between galaxies. Good night.